Dear laureate, dean, professors, ladies and gentlemen, each year we gather to celebrate and honor Christian Birkeland by presenting the Birkeland Award. At Yara, we are proud of our heritage. Christian Birkeland's scientific achievements led to what had been called the most life-saving innovation in history, mineral fertilizer. Billions of lives have been saved. According to the United Nations, half of the world population has food on the table thanks to the invention Birkeland pioneered. Half of the world's population. That's quite extraordinary. For me personally, it brings a sense of purpose, the feeling that what I do, how I spend my days, genuinely matters. I have worked for Yara for 40 years. In that time, I have witnessed a remarkable change. What used to be about volume of fertilizer, volume of grain, volume of food, is today about how. How things are produced, the quality, and the carbon footprint. At Yara's Technology Center, we invent. 20 years ago, we developed the laughing gas catalyst that now reduces about 30 million tons of CO2 equivalents from nitric acid plants emissions globally every year. That was a result of a single scientific breakthrough, developed in Porsgrunn. The breakthrough took years of dedicated work. From my own experience, I know that Yara's pursuit of sustainable farming is driven by knowledge and technology. Progress in science and technology is essential for our success. That is why we support scientific achievements. This is why we honor Dr. Maria Markova. Her doctoral research spans a broad spectrum from nuclear physics to astrophysics, using experiments and theory to explore how elements in the universe originated. Her work is driven by curiosity, without immediate concern for application. And history has shown us curiosity leads to innovation that benefits humanity. A great example is Christian Birkeland. While demonstrating an electrical cannon, he provided the method to Mr. Eide to extract nitrogen from air, now known as the Birkeland-Eide process. This revolutionized the fertilizer production, led to founding of Hydro in 1905, and had a lasting impact on the global agriculture, even though Birkeland's primary goal was to found his Aurora Borealis research. For a better world, every piece of knowledge that can help transform the food system is welcome. Now, this is how Yara can responsibly feed the world and protect the planet. We are here today to recognize and celebrate the scientific excellence, and to celebrate the power of curiosity. Dr. Maria Markova's work reminds us that curiosity-driven research can lay the foundation for a breakthrough that shape our future. Her discoveries challenge traditional knowledge and have motivated scientists to seek alternative explanatory models. And by this, I will give the word to the jury's justification. Professor Magne Guttormsen, please.
ladies and gentlemen, how have the stable elements that we see around us been created? And how have the variants of elements, the isotopes, been formed? The atomic nucleus, I think you know, is composed of protons and neutrons, and we call these entities for nucleons. The lighter nuclei are created in stars and supernova explosions, and the most heavily nuclei, with about 200 or more nucleons, like gold, lead, uranium, are the result of extreme cosmic events, like collision between two neutron stars, or neutron star in collision with a black hole. So in the process of making heavier nuclei, the nucleus must capture neutrons from the hot stellar environment. Usually the neutrons only touch the nucleus and go out again. So the probability for the neutron to be captured in a nucleus depends on the number of available quantum levels in the nucleus, and also that the nucleus can emit gamma radiation. To understand this neutron capture process, Maria Markova has performed several experiments at the Oslo cyclotron laboratory. Based on these results, she can predict the production and abundance of different isotopes on Earth. Maria has focused on thin isotopes, studied as a functional number of neutrons. In the thin isotopes, there are resonances that absorb or emit gamma radiation. These are called pygmy resonances and is very essential for the nucleosynthesis. It has long been believed that these are due to an excess of neutrons oscillating like a neutron skin against the core of equal number of protons and neutrons. But in her study, she has studied 11 thin isotopes, there are no signs that the number of neutrons enhances such a neutron skin resonance. This is very surprising and contradicts the well-established understanding of neutron oscillations. Markova's doctoral work spans a very wide field. She employs experiments and theories from nuclear physics to understand how the elements have originated. In this borderland between nuclear physics and astrophysics, the micro world and the macrocosmos are connected. At the same time, Markova searches for the fundamental physics that govern the micro world. This interest is motivated by scientific curiosity and not possible applications. However, history shows that unexpected fundamental discoveries can indeed lead to new applications for the benefit of humanity. There are one key assumption used to study these resonances, namely the Brink-Axel hypothesis. It states that the same type of resonances can be built on all states in the nucleus. Markova has addressed this in her dissertation by comparing results obtained from proton studies at the Research Center for Nuclear Physics in Japan with experiments at the Oslo cyclotron laboratory. In the energy regime for the creation of heavier atomic nuclei, the Brink-Axel hypothesis works very well, thus simplifying the theoretical description of nucleosynthesis. In her dissertation, she is the first author of 5 papers published in top journals such as Physics Review Letters, Physics Letters B, and Physical Review C. It is worth noting that she has published 1 paper without her supervisor. In this work, Markova collaborates with two of the leading researchers in the field, namely Professor Elena Litvinova from Western Michigan University, United States, and Professor Peter von Neumann-Kosel from Technische Universität Darmstadt, Germany. This shows that Markova has already become an independent researcher who can define her own scientific problems of interest. Furthermore, in her work, she has engaged researchers from South Africa, the US, Germany, France, Belgium, Poland, and of course in Oslo. In conclusion, Maria Markova is a researcher in the true spirit of Birkeland. Her leadership skills, interdisciplinary breadth, and collaboration with the world's leading scientists in the field have been crucial to the outstanding research of her work. She is therefore a very deserving winner of the Yara Birkeland Prize of Physics 2025. Thank you.
It's a true honor for me to hand out this award, this 2025 Yara Birkeland Award to Dr. Maria Markova.
Good afternoon, everyone. So, even though I have already been introduced, my name is Maria Markova, and currently I'm employed as a postdoctoral researcher in experimental nuclear astrophysics in the nuclear physics group at the University of Oslo, and also at the Norwegian Nuclear Research Center, which is relatively new. So, first of all, I would like to express my deepest gratitude for nominating my Ph.D. work for Yara's Birkeland Prize in chemistry and physics, and to the committee for the acknowledgement of my research work at such a high level. Today I was given a rather challenging but yet somewhat exciting task of introducing my PhD work, which was defended on 15th of May 2024, and which was titled Approaching the Pygmy Dipole Resonance in Teen Isotopes with the Oslo Method. So today I would like to present a slightly more simplified version of what Magne has already presented. Even though the primary focus of my work is on investigating nuclei, nuclear properties, I would also say it is also in the field that we would call nuclear astrophysics. So what is this field about? To understand that, we would have to take a look at the periodic table that we all have at some point in our lives, maybe briefly at school, been introduced to. In fact, it includes much more than we are able to naturally observe on Earth, and essentially the whole last period has been synthesized in labs to just simply understand how far we're able to push the limits of science and our knowledge. Well, for us, nuclear physicists, unfortunately, the periodic table is not enough, and what we're a bit more used to working with is the so-called chart of nuclei, which not only shows the chemical element, which is here on the y-axis, but also different isotopes of chemical elements. So the same chemical element, same number of protons, different number of neutrons, different masses. So instead of 118 elements, several thousands of nuclei is essentially our playground. So every single tiny square in this chart is a nucleus with its unique properties. And way less than 10% of these nuclei are nuclei that we can say that we know more or less well about, or their properties. Well, one of the fundamental questions in modern science is, where do all these elements come from, or where do these nuclei come from? So I'll try to present it as a little story for you. So, of course, the only thing we know for sure is we and everything that surrounds us once used to be stellar matter, or in a way, we still are. And So for us, nuclear astrophysicists, the task is to investigate the processes that are responsible for the production of the elementary blocks that we consist of. Those processes we usually call nucleosynthesis. Sometimes when we discuss the element production, we have to look as far back as the Big Bang, which in a way initiated production of protons and neutrons that at some point of time started interacting with each other once the universe has expanded enough and cooled down. And that's when we say that nucleosynthesis begins. Well, in all possible interactions of protons and neutrons, we essentially get all the lightest elements. So if we were to look at these elements, so here every single square is a nucleus from hydrogen to beryllium. This would be an approximate, still quite complex sketch of all possible reactions that protons and neutrons and light nuclei can be engaged in to produce everything up to beryllium. So if we look back at this nuclear chart, at the Big Bang stage, we're still quite far. We're at the very bottom. What about slightly heavier nuclei? Well, to understand where they come from, we would have to take a look at different processes happening in the stars. So if we start with a collapsing gas cloud, which gives rise to a new star. So this star goes through several stages of burning, starting from the lightest elements, essentially hydrogen. Nuclei start fusing with each other to produce heavier and heavier and heavier and even heavier nuclei up to iron. And maybe the star is heavy enough, it has enough iron, and it simply explodes, and we would record this event as a supernova. So coming back to the nuclear chart, well, through all the stages in stars, we managed to climb up to iron. But now the question is, what about heavier nuclei? Where do they come from? Well, it turns out that we can simply start with nuclei around iron and add more neutrons to this nuclei. So, in other words, this nuclei are produced in the so-called neutron capture reactions. Well, I used the word simple. It's not exactly the word to use when it comes to nuclear astrophysics. Where do these neutrons come from? Do we have enough of these neutrons? Those are the questions we have to deal with. Well, in fact, depending on how many, in a way, neutrons we have, we sometimes distinguish between the rapid and the slow process. In the rapid, we have a violent, explosive scenario. It happens within seconds. We have a lot of neutrons. All of them are captured by nuclei around iron, and we produce the heaviest, most neutron-rich nuclei. If we don't have enough neutrons, maybe somewhere in the stars, this process can take up to millions of years. It's rather slow. And we don't really go too far. We stay somewhere close to stable nuclei. So here in the chart, they're marked with these black squares. Sometimes we can distinguish something in between. This is, in fact, a very, I would even say, fashionable topic of discussion in nuclear astrophysics as of right now. But it doesn't matter. What we understand is that the heavier we want to go, the more neutron-rich we want to go, the more neutrons we need. But where do we get them? Well, our colleagues, astrophysicists and astronomers, on August 17th, 2017, recorded the first signal from a gravitational wave and also electromagnetic signal at LIGO and Virgo laboratories in Europe and the US. And this signal comes from two neutron stars merging together. So this would be an excellent site that provides us with enough of neutrons for the creation of heavier elements. Well, in fact, it's also the first ever recorded site of this kind. For us physicists, it's an absolute luxury to be able to observe something we're studying, so we all were immensely inspired by this event. But, oh my God, I'm so sorry. But what do we, nuclear astrophysicists, do? Well, we actually help astrophysicists simulate these processes or describe them better. And here I wanted to just simply show an example of this simulation that was done by our colleagues. So here you can see the same chart. We start somewhere around iron. All these nuclei grab more and more neutrons. They become more neutron-rich, more unstable, and at some point they just simply decay back until they become stable. Well, this simulation looks quite complex, and in fact it is, because It includes, well, maybe I lied here a bit, not exactly 3,000 nuclei, but around that number, the same order of magnitude. It includes a lot of nuclei and tens of thousands of reactions. So for us to even be able to approach the simulations, we need to know. We need to know what happens at this astrophysical sites where these processes take place. What are the temperatures? Do we have neutrons there that we need? We also need to know properties of all of these nuclei involved in the reactions. And this is in fact what I was focusing on in my PhD work, and this is also what quite a lot of my colleagues at the University of Oslo and also cyclotron laboratory are currently working on as well. Well, as you probably have already guessed, one of the, I would say, major directions of research at the Oslo cyclotron laboratory is investigating nuclear properties for astrophysical purposes through experiments. So the very basic idea of the experiments that we are working with is the following. So we start with a nucleus of interest. We bombard it with light particles, maybe protons. It can be something else, for example, helium ion, accelerated by our very old but deeply beloved cyclotron. Yes, we need money for a new one, so I'm... The nucleus gets excited, or as we would say, it moves to a higher excited state in which it cannot stay for too long. It has to release this energy, and so it does by emitting light particles and photons. Well, these particles we actually detect without our detectors or detecting systems. So particles are detected by the detector we call Siri that you can see in the photo here. Well, in fact, you also can see a target holder with some of the targets that we're using in the experiment. And photons are recorded by our so-called scintillator detector array, OSCAR. It's essentially a huge ball of detectors that surrounds a target. So all experiments for my PhD work were performed at the Oslo cyclotron laboratory, which is in fact located in the cellar of the physics building. Well, all these particles we record the information they carry, such as their energies, their directions. Everything helps us learn something about the so-called excited states of the nucleus. So here they are marked with this horizontal blue lines. Well, the higher we go in excitation energy, the more of these excited states we get, the more complex the whole situation becomes. So what we are basically working with is a nucleus that is left in one of these excited states after interaction with a light particle, and it has to decay back to the so-called ground state by emitting photons. That's our, in a way, starting point. So, and what we do is actually we apply the famous Oslo method. I can say it's famous because definitely it is now, at least in the nuclear physics community. It was developed here in around 90s, and I think it got more or less finalized by the year 2000. And this method actually allows us to learn more about the density of this excited state. It's something about their decay properties. So what I was specifically focusing on in my PhD work is using these decay properties to learn more about the so-called pygmy dipole resonance. As Magne has already mentioned, this mode or excitation is believed to occur in heavy neutron-rich nuclei, and it was also, or it is still believed to be caused by oscillations of the nuclear core, equal portions of protons and neutrons, against the rest of the neutrons that form some sort of a cloud or a neutron skin around this core. It is quite interesting from the astrophysical point of view, since it turns out that the equations we would use for the description of this so-called neutron skin are quite similar to those we would use for the description of, for example, neutron stars. It is also it has also been shown that if a nucleus can be found in such a state, it's more likely to grab more neutrons. So in a way, presence of this so-called pygmy dipole resonance in the nucleus is it acts as a booster or it can, in a way, speed up the neutron capture process and therefore production of heavy elements. So even though it's called pygmy, the role of it is quite, it's definitely not pygmy. Experiments focusing on investigating this mode and its astrophysical implications led to me writing this PhD thesis and also several publications that we've been publishing since 2021. Well, in fact, every year. And among the most important findings, I would say, first of all, our experimental results challenged this picture quite seriously, and I would say this picture is still very popular among both theorists and experimentalists in the nuclear physics community. So our latest publication definitely triggered some new debates. At least I hope so. But most importantly, the nuclear properties that we extracted in these experiments. So here I just show the nuclear level density of excited states. It's this narrow blue band, and the so-called gamma strength. You can think about it as the probability of a nucleus to decay with a photon of a certain energy. So this blue band. So our experimental results allowed to significantly reduce exceptionally large currently available theoretical uncertainties for these quantities that we use for astrophysical simulations. So the problem is that all theories disagree with each other, they disagree with the experiment, and we end up with this very broad uncertainty bands, which would, in a way, drag along in our astrophysical simulations. So using our experimental results, instead of working with this enormous uncertainty band, we would end up with something much more narrow. So I would say that the main outcome of my PhD work is us being one microscopic step closer towards a more accurate reproduction of processes responsible for the production of elements, heavy elements, in the universe. And of course, I'd like to use this opportunity to thank my fantastic supervisors, Professor Anne-Cecilie Larsen, who is here today, Andreas Görgen, and Frank Lionel Belgarotte. Without them, this journey would not have been possible. Of course, my colleagues for their support and help, our fantastic cyclotron engineers. Also, once again, without them, these experiments would not have been possible. And also, I would like to thank our collaborators from other universities who helped us with discussions, calculations, also have been inspiring me throughout this PhD years. And of course, to my loving family for their infinite support. So thank you so much for your attention.